Okay, hello, welcome everyone back our class. So this is the second part for the lesson, how to define and display the one qubit quantum state. So, but this part we will look more detail after we have a vector and we have the quantum value, how you can display, and we have collect the probability for the quantum state. So, okay, this is the first time you can see have one problem in the quantum. It's called the collapse. How is collapse? For example, if the quantum to the quantum bit, the qubit can run like this. Is similar is the two qubit is never can meet each other, right? So that is kind of independent. But if something the qubit something this size state and this kind of state, so run together and sometimes something like this. So something have a problem about they will meet each other and try to collapse. So that's the kind of one the big problem in the quantum. You have to make sure to this the qubit it run independent like this, so and it's never meet each other, right? But something is a qubit like this run something they will meet each other and try to collapse. Yeah. So in the quantum simulation, so we will try to simulate one that's okay, and we see how probability for the collapse. So this is kind of code to tell you, to illustrate or to visualize the code, how the quantum the collapse look. And you can see over here we have 3 or 4 the important the comments. First is you can define the one state of vector in quantum state, and the second we can show the probabilities statistic for in the 1,000 sample in 1,000 samples. And we can after the third and the fourth we can display about the statistic the value, and we can plot in the one histogram. So let us see how it looks. This one is a result in the simulation. But one of thing in this kind of result, the number for the qubit 0 and number qubit 1 may be different after every running. So I will show you indirectly. If you see this one is qubit 0 is a kind of probability maybe can up to about 531, right? But about the qubit 1, the 469, right? This one is our random check, and now we can check directly in the screen and see how it is. So we can copy and this code. And you can create a new one, and you can copy over here and click run. So if you see the number for the state for qubit 0 and number for qubit 1, it's different from the our result on the slide, right? This one is different, right? So why? I would say this kind of random, because we can have a random sampling, so the number of course is different. So if you run in your code and you see the number is different from us, that's fine. Yes, that's fine. Don't worry. Okay, so that's it for collapse simulation. We have besides we have for collapse simulation like this, we can simulate some the operation of unitary operator. We will discuss about this detail later, but the first one, this one is a Pauli operator. The second Pauli Y, and the third one is Pauli Z, and the fourth one is this guy of Hadamard operator, and this fifth, that is kind of safe, and the last one, this is T. Actually, we will introduce later about this operator. Just one point, you mean in the collab you can simulate this guy, this kind of basics operator. So you cannot see after you run this code, the output will be show you about the the quantum state. Have a two value, the qubit 1 and qubit 0. So that is a reinforce one of the very basic thing in the quantum computing. In quantum, different from the classical the computer, in quantum you can maintain two values together. That means the 0 and 1 together. And that is one of, I think, one of the big advantage in the quantum computing, because they can run the parallel, the computation. That is one of very good thing. And if you, I will run directly in the screen for let you see, and I can copy code, and I create a new tab, copy, and try to run. And you see, yes, the result is very similar like on the screen. So this is for how to simulate the operation for unitary operator. We'll look back this part in the the next chapter later for how to to sort for each part. And here is how to you can build the quantum circuit. This is very important, the basics in the quantum, because you can create about the several circuit, and you can sort add more about the gate, add more gate for each circuit, and simulate how the quantum process the data. For example, in this model can show you about the order for each gate for the Hadamard gate, and this T gate, this Hadamard gate, this T gate, and the Pauli Z gate. So actually, this part can tell you how to you sort the order, and you can visualize. So this code from this code very simple and can help you to add the new gate. And you will see the on the code is very important. You can sort by order like this circuit. This one you can add circuit 8. Now this Hadamard gate. You can see this and ET you can add something like this. Sorry. And 8 you can see this one. So, this kind of value, the value you can add more, and after you draw, this kind of only show you how to design the circuit. When run on the the collab is the same. So I can show you. It's the same. I think the same. The result. So you can add more pairs and you can run. You see it's the same value, right? And in this example, so you find a gate add to the quantum circuit, the quantum circuit. And about the computing with the circuit, after you add add the new gate, we add a 5 gate. This one we have 5 gate, right? And we can add the input data is called over here. We add the cat 0, or we add the qubit 0, and put the qubit 0 to the circuit and try to process. So this one is add to cat 0 or the qubit 0 to the circuit, right? And try to draw how it looks. So this is the result. The result after you the process or you compute the input data to the the quantum circuit you just built. Okay, this one is an example very similar on the on the collab. So we will next to the next part we will try to summarize and try to see after you compute the input data. So how the probability for qubit 0 and qubit 1 after you calculate the value from from the input. So this is a formula or this kind of code. Yeah, this kind of code. This kind of code can simulate the statistic. Yeah, this statistic. If you see in previous part, I already introduced how you can the statistic, the value for the sampling the qubit 0 and qubit 1 from the calculation. So this kind of code. So if you see over here, we can have a result. Yeah, we have a result for the qubit 0 and qubit 1. Actually, it's the same similar like the previous part. I already showed you the number for qubit 1 and qubit 0 in the sampling will be different after every run. So if you see the number in this slide may be different from the jaw running, so don't worry, that's fine. Okay, so I can show you directly, yeah, something like this. I can run and see how the result is different. So yeah, you can add one more, yeah, and try to run. If you see this is 3,409, right? And if you see in the hour running in this one, it's 3,464, right? So different from the this is a second running. So, but that's fine. Do not worry because this kind of random. So after every running, so the result may be different. Yeah. Okay, so in this lesson, I already tell you how to simulate some the collapse. Yeah, the collapse, simulate the collapse, the phenomenon, and the state, and try to tell you how to the statistics, make a statistics for qubit 1 and qubit 0 in the sampling. And the last one I tell you very important. The value after every simulation running for the probability statistic will be different. So don't worry. Actually, that's a kind of random number. Yeah. Okay. So I hope everyone can got the point. Yeah. Thank you, everyone.